Now we will look at the effect of resonance. So as mentioned before, we'd expect to see a carbonyl around 1700. Of course, it depends on the type of carbonyl. For a typical ketone, around 1708 to around 1720. But that's a typical ketone. So in the case of pentane 3-one, which is a typical ketone, 1716 centimeters to the -1 makes perfect sense to see this very obvious signal. And so what I'm referring to, of course, is this guy here. And so when you see the signal in this region, you'll know that you've got the carbonyl. This will be a very common signal to pick out. We have the same signal in the infrared spectrum corresponding to pent-1ene 3-one. But notice that the frequency or the wave number has shifted to a lower frequency. And so if you're trying to identify this functional group, and you might be saying, well, why isn't it showing up around 1720? You can justify why by realizing that this C double bond oxygen is next to our alkene structure here. And that makes a difference. Let me explain why. And this has to do with resonance. Now, we introduced resonance at the beginning of this course. A little bit later, we're going to explore in great detail various kinds of resonance. But at this stage, let me just point out to you that we can draw a resonance form, although it's not going to be a major contributor. Where the oxygen now will have a negative charge. There'll be a pi bond here, and as a result, there's a positive charge on the N carbon. So as I say, this is not a major contributor, but there is some degree of delocalization of the electron density. Notice that in this second resonance form, what we have in terms of the carbon-oxygen bond is what appears to be a single bond. Now, of course, it's not that the structure is oscillating between these two different forms. The actual structure is a fusion of both. But we say that there's some single bond character associated with the carbon-oxygen bond. And therefore, it's not a full carbon double bond oxygen. Remember that this can impact, therefore, the force constant, because there's now some single bond character. This will decrease the force constant and therefore decrease the wave number where we'd expect to see the signal. So therefore it makes complete sense that the signal is going to occur less than the 1710 or so, and down now into the high 1600 centimeters to the -1. So that's an effect of resonance. I will also point out to you that we do see another signal here. So let me just change my pen color. And I mentioned this when we were looking at the chart. This signal corresponds to a carbon-carbon double bond. And that's very characteristic to see it around the 1640 to 1680. And indeed, this is here. So we've looked at, in this video, the effect of hybridization, the effect of resonance. Let us now examine the effect of signal strength. So you may have noticed as you start to look at these spectra that some signals have very large peaks, some signals have kind of small peaks, and you might be wondering, well, why is this the case? These two examples start to give us a sense of what impacts the signal strength. So once again, we're looking at the pent-1ene 3-one. So let me draw out that structure. What's characteristic about the structure, of course, is the carbonyl group and the alkene. And then we have 2,3-dimethyl-2-butene. Now, of course, the second structure doesn't have a ketone group, but it does have an alkene. And so we've got an alkene here and an alkene here, And as I mentioned in the earlier slide, this signal that's occurring around 1640, it looks like, that corresponds to the C double bond C signal. Clearly, our 2,3-dimethyl-2-butene also should have a carbon double bond carbon signal around the 1640 to 1680 region right here. Now, if you suspected that your structure was 2,3-dimethyl-2-butene and you run the spectrum and you say, wait a minute, what's going on? I don't see the signal. It's important to understand that in order for a signal to show up, the absorption must result in a change in bond dipole, even if it's a really small change in bond dipole. If the bond is completely symmetrical, there is no change in the bond dipole. Therefore, there'll be no absorption, there'll be no signal. Now, I realize that you might be wondering, well, what do you mean change in bond dipole? Because right here, we just have carbon-hydrogen bonds, and how could, when energy is absorbed, there be a change in bond dipole? Well, even a carbon-hydrogen bond is slightly polar. So I realize that when we're talking about polarity, we ignore the polarity of a carbon-hydrogen bond. That is when we're talking about intermolecular forces and polarity. But in terms of infrared spectroscopy, there'll always be a change in bond dipole unless it's perfectly symmetrical about that bond, and therefore there'll be no signal. You may run into some examples later on then when you're trying to interpret spectra and you're looking for a signal and it doesn't actually show up. In terms of this idea, it's also worth mentioning that notice that this signal corresponds to a C double bond O carbonyl group. And look at the size of that signal. This signal right here corresponds to a carbon-hydrogen where the carbon is sp3 hybridized. Notice that although there's only one C double bond oxygen bond in our molecule on the left, where there are multiple carbon-hydrogen bonds in our molecule on the right, the signal is almost the same size. Why is that? Well, notice that the change in bond dipole with a carbon-hydrogen stretch is actually going to be pretty small, whereas a change in bond dipole for carbon double bond oxygen, given that's a very polar bond, well, the change in the bond dipole will change tremendously with the absorption of infrared radiation. Therefore, the more polar bond will tend to give larger signals. So that's another outcome of realizing that there must be a change in bond dipole for an absorption to occur. As the last part of this particular video, I'd like to point out that if the bond in question involves a hydrogen and that hydrogen can make hydrogen bonds, we will expect a relatively broad signal. So as mentioned before, this signal that's happening around 3200 to 3600, this corresponds to the oxygen-hydrogen stretch of a typical alcohol. So this corresponds to butane 2-ol. As you know, hydrogen and oxygens can be engaged in hydrogen bonding with these alcohols, and this gives rise to that very broad stretch. One of the things that chemists will do when they're trying to research this sort of thing is they'll dilute the solution in a solvent, and as the solution becomes more and more dilute, you'll see that this signal becomes more and more narrow. So this is how they know that the broad signal has to do with hydrogen bonding. Look at this next signal, where it almost starts around 2200 and appears to go almost to 3600. Buried beneath this very broad signal, which is essentially what I'm outlining right here, is also the carbon-hydrogen, where carbon is sp3 hybridized. This very broad signal is characteristic of the OH group in a carboxylic acid. And so you can see that both of these spectra represent the signal for an OH group, but the one on the right corresponds to the carboxylic acid. Another telltale sign is, note that we've got this amazing carbonyl stretch right here. So two reasons for knowing that, of course, this corresponds to the carboxylic acid. And we will be doing some practice in our synchronous classes of looking and distinguishing spectra that involve alcohols and spectra that involve carboxylic acids. That very broad stretch, or very broad signal, corresponds to the fact that many opportunities for hydrogen bonding associated with this OH group.